Hello everyone and welcome to my channel Chemistry by Miss Nidhi Banga. Today we will be talking about reasoning and conceptual questions from the chapter Aldehyde Ketones and Carboxylic Acids. So let's get started. Okay, so the first question is compare the solubility of ethanoic acid and benzoic acid in water. So this is your ethanoic acid. You know that this is a component of vinegar and vinegar is basically ethanoic acid and water. So we know that this is very much soluble in water. Okay, now we'll see why. So this in red are water molecules and in black are ethanoic acid molecules. So as you can see that there is a possibility of hydrogen bonding between them. Okay, hydrogen bonding between the partially positive hydrogen and partially negative oxygen. Okay, so that is why ethanoic acid is very soluble in water. Talking about benzoic acid also has every possibility of making hydrogen bonds, but there is a very big and bulky R group here, and this is R groups are hydrophobic. Okay, it's hydrophobic. That means, as the word suggests, it repels water. It doesn't allow water to come close. If water doesn't come close, how would it make hydrogen bonding with water? Right? That is why benzoic acid is insoluble in cold water. You'll have to give it energy to make it soluble. Moving on to the next question. Aromatic carboxylic acid do not undergo Friedel-Crafts reaction. So this is carboxylic acid. First thing that why it doesn't undergo Friedel-Crafts reaction is that it's deactivating. Friedel-Crafts reaction is electrophilic substitution, right? That means an electrophile would get substituted over the benzene ring. But this carboxylic acid group pulls the electron density from the benzene ring, making it less electron dense. Therefore, the electrophile would not be as much attracted to it. So that's one reason. Second thing is that Friedel-Crafts reaction basically uses anhydrous AlCl3 as catalyst because this is a Lewis acid. But your benzoic acid makes a complex with it, so it consumes it. Therefore, aromatic carboxylic acid, that is benzoic acid, would not undergo Friedel-Crafts reactions. Moving on. pKa value of 4-nitrobenzoic acid is lower than that of benzoic acid. Now, first of all, let's clear what pKa means. Ka is directly proportional to acidic strength. Higher the Ka, higher the acidic strength. And since pKa is negative log of Ka, higher Ka would mean lower pKa. So basically, lower pKa means greater acidic strength. So if pKa value of 4-nitrobenzoic acid is lower, that means 4-nitrobenzoic acid is actually stronger acid than benzoic acid. Now, when we talk about acidic strength and factors that influence acidic strength, basically any substituent which increases the polarity of this OH bond increases the acidic strength. Now, any electron withdrawing group would do so. Why? Because electron withdrawing group would pull electron density and therefore from every bond, and therefore this oxygen would pull electron density from OH bond, making it more polar. Okay, so that is why any electron withdrawing group as substitution would increase the polarity of OH bond and therefore increase its acidic strength, therefore decrease its pKa value. Moving on, arrange the following in increasing order of pKa value. Again, increasing order of pKa value, meaning lower pKa value first, that means most acidic first. Okay, so we are going from most acidic or lower pKa value to least acidic or higher pKa value. Now, if you can see, here we have bromine as substituent. Bromine is an electron withdrawing group, and like I said, any electron withdrawing group would increase the polarity of OH bond and therefore will increase the acidity. Here also we have bromine, only one bromine. But here the bromine is a little away from the OH bond. As the distance increases, the effect of electron withdrawing group would decrease. Therefore, since this bromine is closer to OH bond, its effect would be more pronounced, making it more acidic than this. Coming on to the next, here there is no electron withdrawing group. Therefore, this is less acidic than the other two. Here we have two alkyl groups giving plus I effect or increasing the electron density and therefore decreasing the polarity of OH bond. Now this effect is opposite than this. Okay. Here also we have R group, but there is only one R group, one big R group. Here we have two R groups. Therefore, the effect would be more pronounced and polarity of OH would be lower because they are giving electrons. So now OH would not require to pull the electron from OH bond. Okay, oxygen would not pull the electron from OH bond because it's getting the electron density from behind, from this alkyl groups, right? So this explains the order of pK value. Moving on, arrange the following in increasing order of reactivity towards nucleophilic addition reaction. Okay, so nucleophilic addition reaction occurs because the carbonyl carbon is partially positive because it's attached to electronegative oxygen. It's doubly bonded to electronegative oxygen. Therefore, there is a polarity here. So nucleophile would get attracted. But in certain cases, the nucleophile would be more attracted and the reaction would go faster than other cases. So here there are three molecules. Let's see in which case nucleophilic addition is higher. Here we have acetaldehyde. Here the nucleophile would be most attracted, or the nucleophilic addition would be easiest because the nucleophile can easily approach this carbon. There is not much steric hindrance. Plus there is only one alkyl group or electron donating group. Electron donating group tends to decrease the partial positive charge on the carbonyl carbon. So if it decreases the positive charge, nucleophile would not be as attracted. But in aldehydes, there is only one electron donating group as compared to ketones, where there are two of them. Two electron donating groups, double plus I effect. That means the partial positive charge magnitude would be lower, right? That means the nucleophile would not be as attracted because the strength or the magnitude of positive charge is much lower. Okay, and apart from that, these two groups create steric hindrance. In aldehyde, there was only one group. Okay, but in ketone, there are two groups creating more steric hindrance, making it more difficult for nucleophile to approach carbonyl carbon. Now, when we talk about acetophenone, what happens here is this carbon-oxygen double bond is in conjugation with the double bond in benzene group, benzene ring. So what happens is resonance happens, and because of resonance, the partial positive charge or the magnitude of positive charge here decreases much more. Now, since there is no or very little partial positive charge here, nucleophile would not be attracted. Plus, there is bulkiness. So approach of nucleophile would also be very, very difficult. Therefore, this order of reactivity towards nucleophilic addition would be this. Okay, here there would be nucleophilic addition would be easiest. Here it would be most difficult. Next question. What is the purpose of ethylene glycol in Wolff-Kishner reduction? So this is your Wolff-Kishner reduction where hydrazine combines with carbonyl carbon and forms this, and ultimately nitrogen gas gets released and we get an alkane. Now here the solvent that we use is ethylene glycol very specifically. Why? Because once this structure is formed, we need to remove nitrogen from this so that alkane can be formed. To remove nitrogen is a gas, to remove that we have to heat it a lot. We have to increase the temperature quite a bit. For that, we need to be sure that the solvent should be strong enough or should be high boiling enough to sustain the high temperature. If your solvent is low boiling, then all the heat would be taken by the solvent to evaporate, right? So to prevent that, the solvent should be high boiling, and ethylene glycol is just that. There is a lot of hydrogen bonding in ethylene glycol, making it a high boiling solvent. Therefore, it can sustain high temperature without getting evaporated, and the high temperature helps in escape of nitrogen gas. Okay, all right. Next question. There are two NH2 groups in semicarbazide. However, only one is involved in the formation of semicarbazone. So this is the semicarbazide and there are two NH2 groups. Which one will form semicarbazone with the carbonyl carbon? This one. Why not this one? Because for the formation of semicarbazone, the lone pair here should be able to attack the carbonyl carbon, right? But This is possible for this second amino group, but not for first one, because lone pair here are involved in resonance because they are in conjugation with the carbonyl carbon. Okay, whereas here there is no conjugation. Therefore, these lone pairs are actually available to attack the carbonyl carbon. Moving on. pH of reaction should be carefully controlled while preparing ammonia derivatives of carbonyl compounds. So when we are making ammonia derivative of carbonyl compound, we have to make sure that the pH is not too acidic and also it should not be too basic. Because if it's too acidic, the amine here, the ammonia derivatives, also are bases. So they will combine with the acid. So our reactant is consumed in making salt with the acid. So the reaction will not go forward. And if the medium is too basic, that means if there are too many OH minus ions, then they will compete with RNH2 to attack here, carbonyl carbon. Okay, in that case also, the effectiveness of the reaction would be lowered. Next question, why esterification needs to be done in a dry test tube? So this is your esterification reaction. It's reversible reaction, and as you can see, water is one of the products. So if you are taking a test tube which has some water droplets, one of the product is already present there before the reaction has even started. So since there is product here in the test tube, the reaction would go backward so as to consume it, right? So we have to make sure that before we perform this reaction, the test tube needs to be completely dry. Okay, moving on. Carboxylic acids, despite having carbonyl group, do not undergo nucleophilic addition. This is our carboxylic acids. It has carbonyl group, which has carbon as partial positive and oxygen partial negative, but it doesn't stay partial positive for too long because the oxygen in carboxylic acid group has the lone pairs which are in conjugation with the carbon-oxygen double bond. So resonance takes place here, and the magnitude of this positive charge decreases. So nucleophile would not be as attracted to this carbonyl carbon. Therefore, nucleophilic addition does not take place here. Next question. State the purpose of barium sulfate in Rosenmund reaction. This is the Rosenmund reaction where hydrogen is passed over palladium BaSO4. Okay. Now, this acts as a poison, a toxin to this reagent. Hydrogen palladium is actually a very good reducing agent, but we want to stop the reaction at aldehyde stage. That is why we need to poison the reagent. Okay, barium sulfate decreases the effectiveness of this reducing agent and therefore prevents the over-reduction. If we don't add barium sulfate, the aldehyde produced would be further reduced to alcohols. Next question, arrange the following in increasing order of boiling point. Butane, which is an alkane, methoxyethane, which is an ether, propanol, aldehyde, acetone, ketone, propanol, alcohol, ethanoic acid, carboxylic acid. So all these compounds have comparable molecular mass. That is why they are being compared here. Okay, because boiling point depends upon molecular mass as well. Okay, so they all have comparable molecular mass. But what is different then? The difference is functional group. So the increasing order of boiling point is this. Why? Butane has the lowest boiling point because it's alkane. There is very little electronegativity difference between carbon and hydrogen. So this is practically non-polar. Since it's non-polar, the only intermolecular force present in butane molecules is van der Waals force, which is the weakest of all. Then we have ether. Ether is polar, but very little. It is polar, but not as much. So there are weak dipole interactions present in ether molecules. Next up, the aldehyde. It is more polar than ether. That is because this bond, carbon-oxygen double bond, it's double bond. That means there are 4 electrons towards oxygen, more towards oxygen. That means the dipole moment of this bond is much higher. Okay, so this compound is more polar than ethers. Now, ketones are more polar than aldehydes. Why? This bond we know is polar. These bonds are also polar because this carbon is sp2 hybridized, which is electronegative. This carbon is sp3 hybridized, which is not as much electronegative. So there is dipole moment in this direction, here also in this direction. So the overall dipole moment is higher, okay, because they are all going in one direction. The same effect is present in aldehyde also, but only once, only from one side. Here, from both sides, it has twice as much dipole moment from C-C bond, okay. Talking about alcohols, we all know that there is significant hydrogen bonding there, which is a very strong kind of intermolecular force. And last but not the least, or actually the highest, ethanoic acid has the highest boiling point because extensive hydrogen bonding is present here. Okay. Moving on. Although phenoxide ion has more number of resonating structures than carboxylate ion, carboxylic acid is stronger acid than phenol. So this is resonating structures of phenoxide ion, and these are resonating structure of carboxylate ion. So carboxylate ion is more stable than phenoxide ion. Both have resonance, but here the contribution of these resonating structures towards the stability is much more as compared to the contribution of these resonating structures. Why is that? It's because these resonating structures are equivalent. Okay, you can see that they are very, very equivalent. Then there is a negative charge which is on the oxygen. Oxygen is more electronegative, so that contributes to the stability. When we talk about phenoxide ions, the resonating structures are not equivalent. Okay, there are non-equivalent resonating structures, and there's a negative charge on the less electronegative carbon, making it contribute a little less to the overall stability of phenoxide ion. So these resonating structures where there is negative charge on carbon and which are non-equivalent, they contribute very little to the stability of phenoxide ion. Okay, moving on. Explain the change in hybridization and geometry during nucleophilic addition of carboxylic group. So carbonyl group is this. Before nucleophile attack, it's planar, trigonal planar, because the hybridization is sp2. There are 3 sigma bonds, so hybridization is sp2. When nucleophile attacks, the hybridization changes to sp3 because now there are 4 sigma bonds. Okay, and since the hybridization changes to sp3, the shape changes to, or the geometry changes to, tetrahedral. Moving on. What is the advantage of using Debye-Lech as reducing agent? The advantage is Debye-Lech is very, very selective. It would selectively reduce cyanides or ester groups. If there are double bond present somewhere in the compound, that will not be reduced by Debye-Lech. Okay. Next question. Which of the following can be nitrated more easily and why? Benzoic acid or phenol? So phenol we know has an activating effect. That means this phenol group, this OH group, increases the electron density on the benzene by showing plus R effect. Okay, so electron density increases on benzene ring. That is why we call it activating. Activating means now that there is much more electron density on benzene ring, the electrophile would be very, very attracted towards this benzene ring. So the reaction would occur very, very easily. Benzoic acid, on the other hand, shows deactivating effect. That means since this double bond is in conjugation with carbon-oxygen double bond, the electron density is pulled out from the benzene ring, making it electron deficient as compared to this benzene ring. Therefore, the electrophile would be reluctant to attack on this benzene ring. Okay, moving on to the next question. Cyclohexanone forms cyanohydrin in good yield, but 2,4,6 trimethyl cyclohexanone does not. So this is a cyclohexanone. The cyanide attacks here and forms cyanohydrin, but 2,4,6 trimethyl cyclohexanone looks like this, which means that there are bulky groups present near the carbonyl carbon, and therefore your nucleophile would not get a good approach, would not be able to approach, and therefore the reaction doesn't proceed. Give the IUPAC name of the only aldehyde which undergoes iodoform test. So for iodoform test, the necessary condition is that it should have methyl ketone group. And since we are talking about aldehyde, the aldehyde functional group is terminal. So this is the only possibility. This is the only aldehyde which will undergo iodoform test. Next, a chemical test to distinguish between formic acid and acetic acid. Now here, most students make the mistake of saying that this acetic acid, since it has methyl ketone group, it will give iodoform test and this will not. But no. Acetic acid does not give iodoform test because in iodoform test you use NaOH, Ni2. NaOH is a base. This is an acid. They combine to form salt. So the reaction doesn't proceed. Okay. So what will we use to distinguish between the two? That distinguishing test is that formic acid actually undergoes Tollens test. Okay. Now Tollens is a weak oxidizing agent. So it can actually oxidize formic acid but not acetic acid, because oxidizing formic acid to CO2 is easy since it does not involve breaking up of any carbon-carbon bond. Acetic acid, if you want to oxidize to CO2, it's not easy, it's not possible by Tollens reagent because carbon-carbon bond cannot be broken by Tollens reagent. Tollens reagent is just not strong enough. Okay, therefore formic acid will give Tollens test, acetic acid won't. Moving on, why orthohydroxybenzaldehyde is a liquid at room temperature and para-hydroxybenzaldehyde is a high melting solid? In such cases, always see if there's a possibility of intramolecular or intermolecular hydrogen bonding. When we talk about orthohydroxybenzaldehyde, what happens is, because OH is in proximity to this aldehyde group, the hydrogen bonding between OH and C double bond O forms. Now, since this hydrogen bonding, this intramolecular hydrogen bonding has happened, hydrogen bonding between this molecule and other of the same kind would not be possible because intramolecular hydrogen bonding has taken place. Now, in case of para-hydroxybenzaldehyde, OH is not in proximity to aldehyde group. So intramolecular hydrogen bonding is not possible. That means there is a possibility of intermolecular hydrogen bonding. Now this intermolecular hydrogen bonding is a strong force. It will keep these two molecules very close together, very strongly held. So you'll have to give a lot of energy to pull these molecules away. So the boiling point or actually melting point, since this is a solid, would be high. Okay, because of the hydrogen bonding, they are close together. So they form a high melting solid. Next question. Tertiary butyl benzene does not give benzoic acid on oxidation with acidic KMnO4. Now we have seen that if you have alkyl benzene and if you treat it with acidic KMnO4 or basic KMnO4 or actually even chromic acid, CrO3, regardless of the length of the alkyl chain, it gets oxidized to benzoic acid. Okay, but this reaction does not take place when there is tert butyl benzene, because see, just notice what is present here and what's not present here. Here you have two benzylic hydrogens, whereas you have none here. Okay, so because of the lack of benzylic hydrogens, the reaction does not proceed. The reaction, for it to proceed further, it requires benzylic hydrogens, which are not present here. Okay, so this reaction doesn't proceed. Arrange the following in increasing order of their reactivity towards nucleophilic addition. So these are the compounds. There is acetophenone, para-tolualdehyde, benzaldehyde, para-nitrobenzaldehyde. So for nucleophilic addition to happen, nucleophile has to approach this carbonyl carbon. Now notice that all of these compounds have benzene ring attached to carbonyl carbon. So what happens is benzene ring reduces the effectiveness because electrons, it sort of decreases the magnitude of partially positive charge on the carbonyl. But that's present in all the compounds. So that cannot be the difference. What else is the reason? What could be the reason? Acetophenone is least reactive towards nucleophilic addition because in here, apart from this benzene ring, there is a methyl group, which is also contributing to the increased electron density on the carbonyl carbon by plus I effect, because this is electron donating group. It's donating electron, therefore decreasing the magnitude of partial positive charge here. Therefore, the nucleophile would not get attracted to this carbonyl carbon. In here, para-tolualdehyde, what happens is there is also a methyl group, but this methyl group is far away. Okay, This is increasing the electron density, but not as much, because since it's far, its impact is reduced. Okay, but still its presence cannot be totally ignored. So this would be less reactive towards nucleophilic addition than a simple benzaldehyde. Now, when there is a nitro group on benzaldehyde, this nitro group is electron withdrawing group. It will withdraw the electron density and therefore will make this carbonyl carbon more polar. Next question, electrophilic substitution in benzoic acid takes place at meta position. For this, you have to draw the resonance structure of benzoic acid. And as you will do so, you will notice that ortho and para positions are getting positive charge. Now, since ortho and para positions are getting positive charge, by comparison, meta position is electron rich. So the electrophile would attack at the meta position. Okay. Last question for the day. Why ester hydrolysis is slow in the beginning but becomes faster after some time? So this is your ester hydrolysis. In the beginning, we have to add a few drops of sulfuric acid. Okay, but as the reaction proceeds, it's generating its own acid. Now this acid will act as a catalyst and the reaction would become faster. So that was all for today. I hope you liked the video. I hope it helped you. And if it did, please like, share and subscribe. And thank you for watching.